class in linear algebra. For today, we will talk about matrices. Matrices is the plural form of matrix. What is a matrix? A matrix is a rectangular array of scalars, in particular numbers or elements from a field, specifically the set of real numbers or the set of complex numbers. The set of real numbers and the set of complex numbers are known as fields. Again, a matrix is a rectangular array of scalars. Scalars are elements of the set of real numbers, or they may be elements of the set of complex numbers. One example of a matrix is this matrix denoted by M. In general, matrices are denoted by capital letters of the English alphabet, and the entries of matrices are denoted by small letters of the English alphabet with double subscripts. But is a specific example of matrix M with entries. The elements, the scalars in a matrix are called entries of the matrix. So the entries of matrix M are 3, -2, 1, 5, 1/2, and pi. And for this matrix, the scalars or the entries of matrix M are elements of the set of real numbers. The size or shape of a matrix is defined as the number of rows and the number of columns. Again, the shape of matrix is given by the number of rows and the number of columns. When you give the shape or size of a matrix, you always start with the number of rows. For this particular matrix M, there are 2 rows in matrix M. And the rows are the horizontal set of scalars. So this is row 1, which we denote by capital R1. And this is row 2, which we denote by capital R2. When you count the rows of a matrix, you always start from the top. So the first row at the top is row 1. The next from the top is row 2. And this matrix M has 3 columns. And you count the columns from the left. A column is a vertical set of scalars. From the left, this is column 1, denoted by C1. And this will be column 2, denoted by C2. And this is the third column, C3. We can specify the size or shape of matrix M by writing M with a subscript 2 cross 3. Thus, for our specific example, matrix M, we say that matrix M is a 2 by 3 matrix. This is 2 cross 3. We do not multiply 2 by 3 and we say 6 matrix. We simply write 2 cross 3 and we read this as 2 by 3. And we write matrix M now can be written as a matrix M with subscript 2 cross 3, which means that the shape or size of matrix M is 2 by 3, which means that matrix M has 2 rows and 3 columns. In this notation, the first number always refers to the number of rows, and the second number always refers to the number of columns. So if you see this notation, this means that M is a matrix with 2 rows and 3 columns. That is why we describe M as a matrix of size or shape 2 by 3. Or we simply say matrix M is a 2 by 3 matrix. We take another example of a matrix, but this time we do not specify the entries of the matrix, but we represent the entries of the matrix using small letters. So we start with matrix A with shape M by N. If we say matrix A is an M by N matrix, then A has M rows and N columns. We take an example. We let A be an M by N matrix. So if A is an M by N matrix, matrix A has M rows and N columns. And using our notation for matrix, a pair of brackets, if A is an M by N matrix, its entries are denoted by small letter A sub ij. The small letters are used to represent the entries of a matrix. For matrix capital A, we represent its entries by A sub ij. The small letter has two subscripts. The first subscript I refers to the row number of the entry. And because matrix A has m rows, the values of I go from 1, 2, 3 up to m, which means that A has m rows. So the value of I, the row number of the entry, can be 1, 2, 3, or up to m. The second subscript J refers to the column number of the entry. And because matrix A has n columns, the value of J goes from 1 to n. For example, if A sub 35 is an element or an entry of the matrix A with size m by n, then this entry of matrix A is the entry in the third row and the fifth column. The first subscript 3 refers to the row of the entry A, and the second subscript is now your J, refers to the column of the entry A. So A sub 35 is an entry in matrix A of matrix A in the third row and fifth column. We now write all the entries of matrix A with size m by n using the notations A sub ij. The entries of the first row would be denoted by A and with the same subscript 1, because the entries in row 1 all belong to row 1. But the second subscript of the entries in row 1 will vary from 1 to n, because the entry here belongs to row 1 and first column. The next entry in the first row of matrix A belongs to row 1 and second column. The next entry is the entry in the first row, the same row, first row, but in the third column. So the first entry in the first row, first column, we write A sub 1, 1. And the next entry in the same first row, we write A1, A sub 1, but is now in the second column, so we write A sub 1, 2. And the next entry here in the first row, but now in the third column, we write A sub 1, 3. After the third entry, because we did not know exactly how many columns there are in matrix A, we write the 3 dots. This is ellipses. And after the 3 dots, we write the last entry in the first row, because it belongs to the same row, first row, we write A1. But this is now the entry in the last column. And matrix A has n columns. The last column is the nth column. So the last entry in the first row and last column is A sub 1n. We write the entries in the second row of matrix A. All the entries in second row of matrix A are denoted by A with the same first subscript up to. but their second subscript will vary from 1 to n because this is the entry in the second row, first column. And this entry is denoted by A sub to 1. This entry in the second row, denoted by this subscript 2, belongs to the second column. So the second subscript is 2. And this is the entry in the second row, denoted by, as indicated by the subscript 2. But it belongs to the third column, hence the second subscript of this entry is 3. Again, after the third entry, we write the ellipses. And after the ellipses, we write the last entry in the second row and last column. And the last column is nth column. Now we write the entries of the third row, and they all have the same subscript 3, but the second subscript will again vary from 1 to n. Now, matrix A has m rows. This is the first row. This is the second row. These are the entries of the second row. This is the third row. After the third row, we write ellipses again. And the last row entries will have the same subscript of m, because matrix A has m rows. So the last row is the mth row, and all the entries in the mth row will have the same first subscript m. But the second subscript of the entries of the mth row will vary from 1 to n. This is the entry in the first column, the last row, mth row, and first column. So this entry has subscript m1. And this will be A sub m2, entry in the mth row and second column. And this is the entry in the mth row, third column. And this entry, A sub mn, means it is an entry in matrix A in the mth row, last row, and nth column, last column. So if you see the first subscript goes from 1, 2, 3, up to m, because matrix A has m rows. And so the first subscript I will vary from 1 to m. 1, 2, 3, up to m. If you count the second subscript of the entries of each row, like in the first row we have 1, 2, 3, up to n, which means that matrix A has n columns. Hence, the second subscript j of this entry, A sub ij, goes from 1 to n. And now this is the matrix A with size m by n with all its entries denoted by A sub ij, where I is the row number that goes from 1 to m because matrix A has m rows, and the second subscript j goes from 1 to n. J is gives the column number of the entry of matrix A, and the value of j goes from 1 to n because matrix A has n columns. Now, these entries A11, A22, A33, and AMN, this would be called diagonal entries if the subscript m and n are equal. If m and n are equal, then matrix A is called square matrix. We now define a square matrix. Earlier, we described a matrix A with size m by n. That means A is a matrix with m rows and n columns. If the number of rows m and the number of columns n of matrix A are equal, then A is a square matrix. If in A m by n, if in matrix A with size m by n, m equals n, then A is a square matrix written as, because m is equal to n, we write now A m by n as A with size n by n, or we simply write A sub n, which if you see this notation, you know that the matrix A is a square matrix with n rows and n columns. And the entries of matrix A are denoted by small letter a with double subscript ij. But now I goes from 1 to n, which means that matrix A has n rows, and j goes from 1 to n, which means that matrix A has n columns. If we write all the entries of matrix A, these are the entries of the first row. The first subscript of the entries of the first row is the same one, but the second subscript varies from 1 to n because A has n columns. The second subscript j goes from 1 to n, which means that A has n columns. And the entries of the second row of matrix A are A21, A22, A23 up to A2n. They have the same first subscript 2 because they all belong to the same row, 2, second row. But the second subscript varies from 1 to n because they belong to different columns, and matrix A has n columns. And these are the entries of the third row of matrix A, the square matrix A, with the same first subscript 3 because they all belong to the third row of the square matrix A. And the last row entries are A sub n1. The first subscript is n, and the first subscript refers to the row number. And because matrix A has n rows, the first subscript of the entries of the last rows are A sub n1, A sub n2, A sub n3 up to A sub nn. Now, these entries, the entries A sub ij, where I is equal to j, such as A11, A22, A33, and A up to A sub nn are called the diagonal entries of the square matrix A. The diagonal entries in general of matrix A are denoted by A sub ij, where I is equal to j. Again, the diagonal entries in general of the square matrix A sub n, which means that the square matrix A sub n has n rows and n columns, and its diagonal entries are denoted by A sub ij, where the subscript I is equal to the subscript j. And these are the entries A11, where I is 1 and j is 1. A sub 22, where I and j are 2. And A sub 33, where I is 3 and j is 3. Up to A sub nn, where I is n and j is n. Those entries A sub ij, where I is not equal to j, are called non-diagonal entries. Again, the non-diagonal entries of the square matrix A sub n, which means that A is a square matrix with n rows and n columns, are the entries denoted by A sub ij, where the first subscript I is not equal to the second subscript j, which means that the row number of this entry A sub ij of matrix A is not the same as the column number of the entry A sub ij of matrix A. And these are the entries A12, A13 up to A1n, A23, A2n. These are the entries, the non-diagonal entries are the entries above the diagonal entries, and the entries above and the entries below the diagonal entries. These entries above and these entries below the diagonal entries are the non-diagonal entries. Like A sub 32, you can see that I is 3 and j is 2, and I is not equal to j. A sub 23 is a non-diagonal entry where I is 2 and j is 3, and I is not equal to j. Now, not every matrix has diagonal entries. Only square matrices have diagonal entries. We now take a particular example of a square matrix. This matrix denoted by capital letter B is a square matrix. It has 3 rows, 1, 2, 3. And it has 3 columns, column 1, column 2, and column 3. The diagonal entries of this square matrix B with size 3 by 3 are 1/2, -2, 0. The non-diagonal entries of this square matrix B with size 3 by 3 are 0, -1, and this irrational real number E. Also 3, -4, and 1/3 are also non-diagonal entries of the square matrix B of size 3 by 3. If the non-diagonal entries are all 0, then the square matrix is called a diagonal matrix. We now define diagonal matrix using our notation in general of a square matrix A with size n by n with 3 columns and 3 with n columns and n rows. If we have a square matrix A with size n by n, which means that the square matrix A has n rows and n columns, and the entries A sub ij, where I is not equal to j, are 0, which means that the non-diagonal entries of the matrix A sub n are all 0. These are the non-diagonal entries because the subscripts I and j are not equal. Then we call the square matrix A sub n a diagonal matrix. The diagonal entries of this square matrix A sub n, or the diagonal entries of this diagonal matrix A sub n, are denoted by A sub ij, where I is equal to j. And we denote these diagonal entries as simply d sub I, because I is equal to j. So the diagonal entries of the diagonal matrix A sub n are the diagonal entries of the square matrix A with size n by n are denoted by A sub ij. But we have the condition the subscripts I and j are equal. Hence, the diagonal entries A sub ij can simply be written as A sub ii, because j is equal to I. And the diagonal entries we now denote by d sub I, where I is 1 to n. And if we know that the diagonal entries of the diagonal matrix A sub n are d sub I, this diagonal matrix A sub n can be written as the diagonal matrix with diagonal entries d sub I, where I is 1 to n, can be written as d1, d2, d3 up to dn. If you see this notation, This denotes a diagonal matrix whose diagonal entries are D1, D2, D3 up to Dn. Now, in addition to the diagonal matrix with property that the non-diagonal entries are 0, if in addition to this condition, the diagonal entries are all 1, which means a sub ij is equal to 1 for all I equals j, those are the entries a11, a22, a33 up to ann. If they are all equal to 1, these diagonal entries are all equal to 1, then the matrix is called an identity matrix denoted by capital letter I with subscript n. Thus, an identity matrix I sub n is a square matrix. It is a diagonal matrix whose non-diagonal entries are 0, but the diagonal entries are all 1. We define identity matrix. It is a square matrix. An identity matrix is a diagonal matrix because its non-diagonal entries are 0, and the last property of an identity matrix is that all the diagonal entries of an identity matrix are 1. And the identity matrix of size n by n is denoted by I sub n. We now state formally the definition of identity matrix. If in diagonal matrix A sub n here is a square matrix of size n by n with n rows and n columns, and it is a diagonal matrix, which means the entries A sub ij of matrix A are 0 for I is not equal to j. And if the diagonal entries of A sub n denoted by D sub I, where I is 1 to n, are all equal to 1, for I is 1 to n, then the diagonal matrix A sub n is an identity matrix denoted by capital I with subscript n. Example, capital I with subscript 2 is an identity matrix of size 2 by 2, which means that I sub 2 here is a square matrix with 2 rows and 2 columns, and its non-diagonal entries are 0 because an identity matrix is a diagonal matrix, and it is an identity matrix is a square matrix. In this case, it's a square matrix of size 2 by 2, and the diagonal entries of the identity matrix I sub 2 are 1. With that information, we write the matrix, the identity matrix I sub 2. This is the identity matrix. The diagonal entries are 1 and 1. And the non-diagonal entries, the entries above and below the diagonal entries are 0. And you can see that this is a square matrix. The non-diagonal entries are 0, and all the diagonal entries are 1. Therefore, this square matrix 2 by 2 is an identity matrix. Without writing the matrix I sub 100, this is a large matrix, you can describe this matrix I sub 100 as an identity matrix with size 100 by 100, which means that this identity matrix I sub 100 is a square matrix with 100 rows and 100 columns. That's the first property of identity matrix. The second property of this identity matrix I sub 100 is that all the non-diagonal entries of this matrix, identity matrix I sub 100, are all 0. And the diagonal, that's the second property. The last and third property of this identity matrix I sub 100 is that the diagonal entries of this identity matrix I sub 100 are all equal to 1. We now define lower triangular matrix and upper triangular matrix, beginning with lower triangular matrix. We define lower triangular matrix. The given here is a square matrix denoted by A sub n with size n by n with n rows and n columns. And the condition for the square matrix to be a lower triangular matrix is that the entries A sub ij must be 0 for I less than j. This means the row number of this entry is less than the column number of these entries. And these entries are actually the entries above the diagonal. The entries above the diagonal entries have subscript with I less than j. And before we give an example of lower triangular matrix, we define upper triangular matrix. And it is just exactly the opposite of this condition, I less than j. For upper triangular matrix, the entries A sub ij of the square matrix A sub n are all 0 for I greater than j. And those entries A sub ij for I greater than j are actually the entries below the diagonal entries. We now formally state the definition of upper triangular matrix. The given here is a square matrix denoted by A sub n, which means that the square matrix A has n rows and n columns. And the condition for the square matrix to be an upper triangular matrix is that the entries a sub ij are all 0 for I now greater than j. And as I said earlier, these are actually the entries below the diagonal entries of the square matrix. And if they are all 0, then the square matrix A sub n is an upper triangular matrix. We now take some examples. For our first example, consider matrix C with size 5 by 5. C sub 5 means that matrix C is a square matrix with size 5 by 5 with 5 rows and 5 columns. And the entries of C5 can be denoted by C, small letter C sub ij. Where the first subscript I goes from 1 to 5, and the second subscript j of C sub ij goes from 1 to 5 also. Because matrix C is a square matrix with 5 rows and 5 columns. And these are the entire square matrix C sub 5 with entries denoted by small letters with double subscript. These are the entries of the first row, and these are the entries of the last row. If you count the first subscript goes from 1, 2, 3, 4, 5 because the square matrix C has 5 rows. If you count the second subscript goes from 1, 2, 3, 4, 5, which means that matrix C has 5 columns. And the diagonal entries are those entries C sub ij where I is equal to j. And those are the entries C11, C22, C33, C44, and C55. Now we tell when this square matrix C will be a lower triangular matrix. And the condition for matrix C to be a lower triangular matrix is that the entry C sub ij the square matrix C sub 5 will be a lower triangular matrix if the entries C sub ij are 0 for I less than j. The row number of the entry C sub ij is less than the column number of the entry C sub ij of matrix C5. And those are C12, the first subscript 1 is less than the second subscript 2. This is C13, C14, C15. All these entries have the property I less than j. The row number is less than the column number. And if all these entries are 0, then we have a lower triangular matrix. Because these entries from the diagonal and the entries below together with the entries below the diagonal will form a triangle. So we call this a lower triangular matrix if all the entries above the diagonal are 0. Those are the entries C sub ij for I less than j, and they are all 0. Then the matrix C5 is a lower triangular matrix. And this matrix C5 is called an upper triangular matrix if the entries C sub ij are 0, but the row number is greater than the column number of the entry C sub ij of the matrix C5. Now, where are these entries? C sub ij for I is greater than j. Those are the entries below the diagonal entries. Those are C21, the row number, is greater than the column number C31, C32, C41, up to C54. These are the entries C sub ij for I greater than j. For the row number greater than the column number, if all these entries are 0, if all the entries below the diagonal entries are 0, then the square matrix C5 is called upper triangular matrix. We take another example. Consider the identity matrix I sub 3. An identity matrix is a square matrix. In this example, it is a square matrix with size 3 by 3 with 3 rows and 3 columns. Another property of the identity matrix is that the non-diagonal entries are 0. The diagonal entries, as the third property says, of identity matrix are all 1. And these are the diagonal entries. The non-diagonal entries are the entries above the diagonal and the entries below the diagonal. And they are all 0, so this identity matrix I sub 3 is a diagonal matrix. Because the condition of the upper and lower triangular matrices are satisfied by the identity matrix. The identity matrix is both an upper triangular matrix and lower triangular matrix. In particular, this identity matrix 3 by 3 is a lower triangular matrix because all the entries above the diagonal are 0. And this identity matrix 3 by 3 is also an upper triangular matrix because all the entries below the diagonal are 0. Hence, the identity matrix is both an upper and lower triangular matrix. But a diagonal matrix is not always an identity matrix. If there is at least one element in the diagonal matrix that is not 1, then it is not an identity matrix. But a diagonal matrix is also a lower triangular matrix and an upper triangular matrix. We take an example. Consider this matrix D sub 3. D sub 3 is a square matrix with size 3 by 3. It has 3 rows and 3 columns. And this is an example of diagonal matrix. The non-diagonal entries are 0. The diagonal entries are 1, 1, negative 1. Hence the condition d sub ij not equal to 0. The condition that the entries d sub ij for I equals j not equal to 0, not all equal to 0, is satisfied. And the entries d sub ij where I is not equal to j are 0 are satisfied also by d sub 3. Hence d sub 3 is a diagonal matrix. In this particular example, the diagonal entries are not all equal to 0. For I equals j, we have the diagonal entries 1, 1, negative 1, and they are not all equal to 0. But these diagonal entries for diagonal matrix may be 0. The only condition for diagonal matrix, for a square matrix to be a diagonal matrix, is that the entries d sub ij for I not equal to j, so these are the non-diagonal entries, must be 0. This is the only condition for a square matrix to be diagonal. But for this example, the diagonal entries d sub ij where I equals j are not equal to 0. But the diagonal entries of a diagonal matrix may be 0. If the diagonal entries of a diagonal matrix are 0, then we call it a 0 matrix. But first, as I was telling you earlier, not every identity matrix is a diagonal matrix, but not every diagonal matrix is an identity matrix. This square matrix is a diagonal matrix, but it is not an identity matrix because one of the entries in the diagonal is not 1, but negative 1. But a diagonal matrix is a lower triangular matrix because the entries above the diagonal are all 0, and the diagonal matrix is also an upper triangular matrix because the entries below the diagonal are also 0. Now we define 0 matrix and symmetric matrix, but I already said that a 0 matrix is a diagonal matrix whose diagonal entries are all 0. We now formally define 0 matrix. A 0 matrix is a square matrix. A 0 matrix is a diagonal matrix. If in diagonal matrix A sub n, so the given here is a square matrix A with size n by n with n rows and n columns. And this square matrix is a diagonal matrix, which means that the entries A sub ij for I not equal to j are all 0. It means that the entries above and below the diagonal of the matrix A sub n are all 0. In 0 matrix, in addition to that, the diagonal entries d sub I, these are the entries in the diagonal. These are the entries A sub ij for I equals j, denoted simply by d sub I, are all 0. Then the square matrix, the diagonal matrix A sub n, is called 0 matrix. This is an example of 0 matrix denoted by Z sub 4 because it has 4 rows and 4 columns. The diagonal entries are the entries Z11, Z22, Z33, and Z44. Those are the diagonal entries. This is a square matrix. This is a zero matrix. A zero matrix is a square matrix with equal number of rows and number of columns. The zero matrix is a diagonal matrix. All the entries above the diagonal and all the entries below the diagonal are zero. And in addition to those properties, the zero matrix has the property that the diagonal entries are all zero. Question: is this an upper triangular matrix? Is this a lower triangular matrix? This is a lower triangular matrix because all the entries above the diagonal are zero. And the zero matrix is also an upper triangular matrix because the entries below the diagonal are zero. Therefore, the zero matrix is both a lower triangular matrix and an upper triangular matrix. In addition to that, the zero matrix is an example of what is called a symmetric matrix. This is the entry in the first row, second column. This entry here is the entry in the first row and second column. And it's equal to 0. And that entry is equal to the entry in the second row. This is the entry in the second row, first column. This entry is 0. This entry 0 is the entry denoted by Z sub 1, 3. This is the entry in the first row and third column. And you can see that this entry Z sub 1, 3 is equal to the entry Z sub 3, 1. Z sub 3, 1 is the entry in the third row, 1, 2, 3, and first column. It's 0. This entry is the entry denoted by Z sub 1, 4. It is the entry in the first row and fourth column. And that entry, Z sub 1, 4 equal to 0 is equal to the entry Z sub 4, 1. Z sub 4, 1 is the entry in the fourth row and first column. 1, 2, 3, 4, and first column 0. This entry is the entry in the second row and third column, or this entry 0 is denoted by Z sub 2, 3. And that entry is the same as the entry in the third row and second column. Third row, 1, 2, 3, second column, 1, 2, 0. And this entry, the entry in the second row and fourth column, denoted by Z sub 2, 4. Is the same as the entry in the entry Z sub 4, 2. And this entry, the entry in the third row and fourth column, Z sub 3, 4, is the same as the entry Z sub 4, 3. P sub 4, 3 is the entry in the fourth row. 1, 2, 3, 4. And third column, 1, 2, 3, 0. And this matrix, because of these properties, is called symmetric matrix. Therefore, the zero matrix is a symmetric matrix. But these entries that are equal are not necessarily zero. They happen to be zero because the symmetric matrix is the zero matrix. We now define symmetric matrix in general. In general, only a square matrix can be a symmetric matrix. A matrix that is not a square cannot be a symmetric matrix. But for a square matrix to be a symmetric matrix, this condition must be satisfied. The entry A sub ij must be equal to the entry A sub ji. Again, for the square matrix A sub n to be a symmetric matrix, the entries A sub ij must be equal to A sub ji, for I not equal to j. As in the zero matrix, here this is the I and j, and this entry is equal to the entry z sub ji, and I is not equal to j. This is I and this is j, 1 is not equal to 3. In this entry, I is 2, j is 3, I is not equal to j, but the entry is z sub ij is equal to the entry z sub ji. And this must be true for all entries A sub ij and A sub ji, they must be equal for I not equal to j. The identity matrix is another example of a symmetric matrix. We take another example of a symmetric matrix and we define Hermitian matrix. We now take an example of a symmetric matrix that is not a zero matrix but it is a square matrix. Consider matrix P. Matrix P is a square matrix because it has 3 rows, 2, 3, and 3 columns, 1, 2, 3. So matrix P is a square matrix of size 3 by 3. And we check the non-diagonal entries. We start with entries above the diagonal. These are the diagonal entries. This is P11, P22, P33, or these are the entries P sub ij where I equals j. And above the diagonal we have -1. -1 is the entry in the first row and second column denoted by P12, and we check if this is equal to the entry P sub 21, This is the condition in the definition of symmetric matrix. The entry P sub ij must be equal to the entry P sub ji. And the entry in the second row and first column, 1, 2, second row, first column is negative 1. And it's equal to P1, 2. Next, we have 2 above the diagonal. We have 2. This is the entry in the first row and third column denoted by P1, 3. And we check if this is equal to the entry P sub 3, 1. P sub 3, 1 is the entry in the third row, 1, 2, 3. And second column, 1, 2. And we are here. 2 is the entry in the first row and third column. We check if it's equal to the entry in the third row and first column. Third row, 1, 2, 3. And first column, 1, 2. So P31 is equal to the entry P13, and they are both equal to 2. And the last entry above the diagonal is 1/2. And 1/2 is the entry in the second row and third column, P sub 2, 3. If this is symmetric, this entry must be equal to the entry P sub 3, 2. The entry in the third column and second row. Third row and second column. P sub 3, 2 is the entry in the third row and second column. 1, 2, 3, second column, 1, 2, 1/2. Therefore, these entries P sub 3, 2 and P sub 2, 3 are equal, and they are both equal to 1/2. And we therefore conclude that the square matrix P of size 3 by 3 is a symmetric matrix. From the given square matrix, it's easy to test whether it is a symmetric or non-symmetric matrix. Draw the diagonal, identify the diagonal entries, and see the symmetry with respect to the diagonal entries. And these are the symmetry. We have -1, -1, 2, 0, 2, and 1/2, 1/2. So this square matrix A is a symmetric matrix. And a symmetric matrix is an example of what is known as Hermitian matrix. And we now define Hermitian matrix. A Hermitian matrix is a square matrix. Thus, in the definition, we are given A sub n, the square matrix A with size n by n. If in the square matrix A sub n, the entry A sub ij is equal to A sub ji bar, then the square matrix A sub n is called Hermitian matrix. This notation A sub ji bar is the conjugate of the entry A sub ij. And we usually have conjugate if the entries of the matrix are complex numbers. If you recall, if the complex number is A plus B I, then the conjugate of this complex number A plus BI is A minus BI. Again, A sub ji bar is the conjugate of the entry A sub ij. And for the complex number A plus bi, where I here is the square root of -1, the conjugate of A plus bi is A minus bi, which means that to get the conjugate of a complex number A plus bi, we simply take the opposite sign of the imaginary part of the complex number. In this complex number A plus bi, A is the real part and bi is the imaginary part because I is equal to square root of -1, and we do not have actually square root of -1. So the conjugate of A plus bi is obtained by taking the opposite sign of the imaginary part bi, and we obtain A minus bi. The conjugate of A minus bi, again we find the conjugate of the complex number by taking the opposite sign of the imaginary part of the complex number. In this case, the sign of the imaginary part is negative and its opposite sign is positive. Thus, the conjugate of A minus bi is A plus bi. Therefore, we can say that A plus bi and A minus bi are conjugates of each other. The conjugate of A plus bi is A minus bi, and the conjugate of A minus bi is A plus bi. Now, we said before in algebra that the set of real numbers is a proper subset of the set of complex numbers, which means that every real number is a complex number, because every real number R, say R, every real number R can be written as a complex number of the form R plus or minus 0i. So R now is the real part and the imaginary part is 0i. But R plus or minus 0i simplifies to R. So this complex number is actually a real number with imaginary part 0i. But if you take the conjugate of R plus or minus 0i, it will be R minus plus 0i, which simplifies to R. Therefore, the conjugate of a real number is equal to itself. So if the conjugate of a real number is equal to itself, then the symmetric matrix is a Hermitian matrix. -1, its conjugate is itself -1. So this entry P sub 1, 2 is equal to the conjugate of P sub 2, 1. And the conjugate of P sub 2, 1, -1 is itself -1. And 2 here is the entry in the first row and third column, and it is equal to the conjugate of P sub 3, 1. P sub 3, 1 is also 2, and its conjugate, the conjugate of 2 is itself, and they are equal. Therefore, the symmetric matrix with entries that are real numbers is a Hermitian matrix. We now take another example of Hermitian matrix. Consider the square matrix H. We verify if the square matrix H is a Hermitian matrix. A Hermitian matrix must be a square matrix. And the square matrix H is a square matrix. In particular, it is a 3 by 3 matrix because it has 3 rows, 1, 2, 3, and 3 columns, 1, 2, 3. Now, we check if this matrix satisfies the property that H, the entry H sub ij, is equal to the conjugate of H sub Ji. For I not equal to J. This means that in checking whether a given square matrix is a Hermitian matrix, we are not interested with the diagonal entries. And the diagonal entries are 2, negative, square root of 2, and the irrational number pi. What we need to check are the non-diagonal entries of the given square matrix. We start with negative 6i. Negative 6i is the entry in the first row and second column denoted by H12. And we need to check if this is equal to the conjugate of H sub 21. H sub 21 is the entry in the second row and first column. Second row 1, 2, first column 1, 6i. And the conjugate of this complex number 6i, as we said earlier, is obtained by taking the opposite sign of the imaginary part of the complex number. This complex number 6i has no real part, but its real part is 0 if you write 6i as 0 plus 6i. The real part is 0. And the imaginary part is 6i. But in finding the conjugate of a complex number, we take only the opposite sign of the imaginary part. And the imaginary part of 6i is itself 6i, and its opposite sign is minus 6i. Hence, the conjugate of the entry H sub 2i is minus 6i. And it is equal to the entry H sub 1, 2. Now, this entry 1 is the entry in the first row and third column. And we have to check if this is Hermitian matrix. We have to check that this entry H13 is equal to the conjugate of the entry H31. The entry in the third row and first column is third row 1, 2, 3, first column 1. And it is 1. The entry in the third row and first column is 1. And as we said earlier, the conjugate of a real number is itself 1. Hence, the entry H13 is equal to the conjugate of H31. And finally, we check this entry if it's and this entry 2 plus 3i is the entry in the second row and third column. If this is Hermitian matrix, this entry H sub 2, 3 by definition of Hermitian matrix must be equal to the conjugate of the entry in the third row and second column. The entry in the third row and second column is 1, 2, 3, third row, second column, 1, 2. 2 minus 3i. And the conjugate of 2 minus 3i is obtained by taking the opposite sign of the imaginary part of this complex number. In this complex number 2 minus 3i, 2 is the real part and minus 3i is the imaginary part, and the opposite sign of the imaginary part minus 3i is plus 3i. Therefore, the conjugate of 2 minus 3i is 2 plus 3i. Thus, the conjugate of the entry H sub 32 is equal to the entry H sub 23. And this property of Hermitian matrix is satisfied. H sub I is equal to the conjugate of the entry H sub Ji. for I not equal to j. Therefore, we conclude that this square matrix H of size 3 by 3 is a Hermitian matrix. And that ends our lesson for today in linear algebra. In the next lesson, we will take some more, the other types of matrices, the non-negative matrix, the positive matrix, a row vector, a column vector. And we will start with the binary operations on matrices. If you have question about the lesson today, you ask your question in the comments below. And thank you for joining me in my class today in linear algebra.